do the same thing for toluene. The boiling point of toluene, we will look up in appendix B1. So let's go back to that appendix. Now we'll be looking at toluene, which is way at the bottom of that table. Yeah, found it. That's toluene. And the boiling point 110.62, the latent heat 33.47. So that's what we're going to write down in our example. 100, oh God, I keep on doing that. That will be 110.62 degrees C, and the latent heat is 33.47 kilojoules per mole. Yeah, we're just getting the values from appendix B1. Now, what we need to do is we're going to get the CPs, the heat capacity. Right? We're going to get the heat capacity for benzene liquid, toluene liquid, and then we're going to do benzene vapor and toluene vapor. We need these values because we're going to do the integration when there is a change in temperature. Okay, so for benzene, liquid benzene, the CP will be for all the CPs. Actually, it should be in appendix B2. So there I have highlighted it from previous example. Yeah, we know that it's going to be using the, it's going to be liquid. It's going to be in the first form, which is that form. Yeah, that's the first form. That is your equation A plus BT plus CT square plus DT to the power of 3. The unit should be in degrees C. And this is your A times 10 to the power of 3. This is your B times 10 to the power of 3. So if you're going to look at the benzene in the gas phase, this is benzene in the gas phase. Again, you're going to use the first equation, same unit. This is your A, B, C, D. Okay? So we're going to write that equation in our example. So I have over here, let me see, this is the equation for liquid. So Cp is equals to 126. I have it wrote down over here so that I don't have to flick back and forth looking at the appendix. So I just jot it down now. You can check whether I got it right based on the appendix. Okay, that's the Cp of liquid benzene. The Cp of vapor of benzene in a vapor phase. So now I'm going to just write it down. That's A. This is B. Right now, everybody should be very familiar with this equation because we have been doing a lot of it. T square, and lastly, the D term. I almost run out of space. Minus 2. Okay. That's your equation for Cp for benzene in the vapor phase. So we do the same thing for toluene. Let's go back to our table. Okay, here we have toluene. We have the gas phase, the liquid phase. This is the gas phase. Same temperature, the unit, the same temperature unit. Same unit, degree C. So I'm going to jot that down. We have the liquid phase highlighted in orange and the gas phase highlighted in red. So let's write that down in our example. For toluene, liquid, 148.8 times 10 to the power of minus 3 plus 32.4 times 10 to the power of minus 5 to the temperature. And for the vapor phase, let's see, 94. I'm not going to write the Cp because I need the whole space. 1.8 times 10 to minus 3 plus 38 times 10 minus 5 T minus 27.86 times 10 minus 8 T to the power of 2 plus that's 80.33 times 10 to the power of minus 12 T to the power of 3. For that over here should be T to the power of 3. Okay. I could at least squeeze it. Let me undo that. Let me start from here. Okay, I'm going to write it all over again. For our, this is benzene vapor, so that's minus 25. I'm going to write all over again because I need some space, which in order to write to fit everything in. Minus 12 into power 3. Okay, done. Okay, everything is there. Now, let's look at what's happening over here. So look at our block diagram. What we have over here is you have liquid. Oops, undo that. We have liquid over here. We're going to change it to liquid at in the bottom face. So liquid to liquid from 10 degrees C to 50 degrees C. No change of phase. Okay, no change of phase. That is just liquid to liquid. So it's just from liquid to liquid. No change of phase. So every time we have a change of temperature without any phase change, without any pressure change, it's just the integration. So let's look which one is involved with liquid. So that is H1 and H2. We need to calculate that. So let's do for benzene first. For benzene liquid, we start at 10 degrees C. We assume at 1 atm. So we're going to start that as our starting point, and we will end up benzene liquid at 50 degrees C. That is the temperature of your outlet bottom product, and 1 atm. So this is your H1. This is your enthalpy cap 2. So if you assume this is as your reference state, which we did earlier, so this enthalpy 1 is equal to 0. So right now we are actually getting the value of H2, which is H2 minus H1. That's equal to 0. So end up with going to. So we already know that whenever there is just a temperature difference, that can be easily calculated from the temperature, beginning temperature to the final temperature. All you have to do is the integrate using the Cp with respect to temperature. Okay, so okay, I better redo my symbol because H1, H2 is going to be confusing if we look at this. That's H2. Sorry, I deleted it. That's H2. I better not use H2. You might get confused. So let me undo that. Let me give it a different value. This is initial. This is final. Okay, so that will be final. That is equals to H1. If you look at the table, that is H1. Right now we are looking at H1. Okay, you're looking at H1 for benzene. Bless it. Ibrahim, are you okay?
Sorry.
Are you having a cold?
No, I'm fine.
Fine, good. Okay, Alhamdulillah. Okay, now, what is your final? This is going to be final. Oh dear. That is final. I'm not going to use subscript 2 because we might get confused. Yeah. What I can, okay, stick with that. So H final, which is according to our table over here, H1. Okay? H1 enthalpy cap 1, okay, is equals to the integration 10 degrees C to 50 degrees C. Okay, now let's look at the enthalpy, the Cp, the heat capacity of our liquid benzene. So sorry. That is the liquid benzene, the Cp of our liquid benzene. So write that down, 126.5 times 10 power negative 3 plus 23.4 times 10 power minus 5 temperature with respect to temperature. So if you do your calculation, this is very straightforward calculation using your calculator. So somebody please try to get the value for me.
I get 5.34.
Thank you. I will write it into 4 decimal places. This is what I got. Okay.
Same.
Yeah, same. Thank you. Okay, so we will write that down in our table, 5.3408. That's the value. We do the same thing for toluene because it's just liquid, no change in phase. and just a temperature change. So for H2, I'm not going to construct I'm not going to construct the diagram because we know what we're supposed to do. It's just from 10 degrees C integration to 50 degrees C. But right now we'll be looking at toluene. So the CP of toluene in the liquid phase is as written here. So I'm going to just copy that inside the equation. 148. Oh, I cannot show both of it at the same time. 148.8. Let me, okay, just copy it from my notes. With respect to temperature, after you have integrated that, give me a value, please. The unit again is kilojoules per mole. Let's make, yeah, what is it?
6.34.
Sorry? Question?
6.340.
6.340. I got 0.08. Okay, same. Anybody getting a different value? Anybody getting a different value? Because, you know, you need to check your calculation.
Same, doctor.
Thank you very much. Thank you, Aiman. Okay, next. H2, H3, and H4. Sorry, enthalpy 3 and enthalpy 4. Now you are looking at vapor, okay, which is what is happening here. From a liquid phase, you're going to change to vapor. This is vapor. This is vapor. So you're going to change it from liquid to vapor. Going to vapor phase. So whenever you have anything that is a change of phase, you know you need to construct your hypothetical path. Okay? So let's start with benzene, liquid at 10 degrees C, 1 atm. That is your starting point. You're going to end up benzene, vapor at 50 degrees C, 1 atm. Okay, we know from our earlier that value that we got from appendix B1, benzene boils, the boiling point of benzene at normal pressure 1 atm is 80.1, and this is its latent heat. So we're going to use that information when we construct our hypothetical path. So you start with 10 degrees C, you need to go to 50. Do you need to go to 50 or do you need to go to another temperature?
The boiling temperature.
The boiling temperature, good. That is 80.1 for benzene. So you need to go to 80.1. Benzene, liquid, no change of phase, 80.1 degrees C, still 1 atm. So that is your second step. Next.
Change in phase only.
Yeah, change in phase. You're going to go to liquid, from liquid to vapor, 80.1 degrees C, still 1 atm. So now, let's say this is going to be a change of temperature. This is a change of phase. Huh? And this is going, lastly, you're going to change it from 80 degrees C. Sorry, I could not get a straight line there. From 80 degrees C, you're going to go to 50 degrees C. Same temperature. Same pressure, same phase. So that is only a change of temperature. Okay? So this is delta H1. This is delta H2. This is delta H3. So that H2 is only a change of phase. So that will be your latent heat of vaporization. So if you write the value which we got earlier.
Doctor.
Sorry, yes.
Is it possible to have at the same pressure to have both liquid and vapor, although the boiling temperature is higher?
Okay, you did ask this question last time, or was it somebody else? Okay, right now you did, isn't it?
Yeah.
The thing is, we are assuming that it is 1 atm. The boiling point is 80.1. By logic, your temperature. Let's see. What was the question again? Is it possible for it to be boiling?
Yeah, I mean the pressure should be lower, right?
Okay, you are looking at this right now. I understand. You're looking at this, isn't it?
Yes.
Yeah.
The final state.
Yeah. Okay. The pressure by right should be lower, then the temperature should be lower also. It's not possible for it to be a vapor at 50 degrees C when its boiling point is higher. You know, the boiling point is higher. By right, it should not be possible if the pressure is the same.
Yes.
Okay, yeah. Okay, I see your logic there. Okay.
Okay, so we just ignore the change in pressure, right? Because we want to include it in the equation.
Yep, because the thing is, the question did not state what is the pressure of the vessel. There's no mention at all.
Uh-huh.
Okay. Normally, if your input is 1 mole, your equipment should be running at a vacuum, in a vacuum state. Sorry, I got it wrong. If your feed is at 1 atm, then your distillation should be running less than 1 atm. Normally, that is what happening in the plant. But in this case, there's no mention at all about the pressure. So we are going to assume it's about this 1 atm because there's no mention. We assume. Okay, we just assume. Because there's no pressure of the outlet. There's no, okay? So we're going to assume. By right, it should be less. Yes, you're right about that. It should be lower than 1 atm in order for the temperature to be lower. Yes, that's right. You got it right there. Okay? There's no way this benzene can exist as a vapor at the same pressure when the temperature is lower than the boiling point. There's no way. Should become liquid again. But right now, this is what we have. So we're going to assume it's the same pressure. Okay, guys? Ayman, is that okay with you?
Yes, Dr. Khalif. Thank you.
Thank you. Okay, so now let's continue. We have a change of temperature over for the first step. For the first step, it start from 10 degrees C to 80.1. So we're going to do the integration based on the liquid CP because your step 1 is both at liquid phases. I mean, the phase is still liquid. There's only a change of temperature. For step 3, you have vapor. So you do the same thing, the integration, starting from 80.1 degrees C, which is your starting temperature, and you end up with 50 degrees C. The only difference is that now your CP will be that of your vapor with respect to temperature. So we're going to do both calculation. Okay. For the second enthalpy change, which is that of phase change, we're going to write down the latent heat of vaporization, 30.765. So that will be 30.765 kilojoules per mole. So the overall change, will be the total of each individual of the steps taken to reach your final conditions. The final condition, sorry. Yeah. So let's do one step at a time. Delta H1, we're going to integrate 10 degrees C, 80.1 degrees C. We are looking at benzene. Is the CP of liquid benzene. So CP of liquid benzene over here, 126.5. I'm going to write that down. 126.5 times 10 power of negative 3 plus 23.4 times 10 to the power of minus 5 T with respect to temperature. So what is your answer, guys? You got to be very familiar with using a calculator in order to get the integration done. Because if you are used to it, practice makes perfect. You should get it done really quick. If I look at my answer, I got 9.6066 kilojoules per mole. Anybody getting a different value?
Same, doctor.
Thank you, Ayman. Okay, you do the same thing for the third step, which is the integration from 80.1 degrees C to the final temperature. But this time we'll be looking at the CP of the vapor. So for benzene, the CP of vapor for benzene, if I highlight it, this is the CP of vapor for benzene. Okay, I didn't do a good job there. Okay, that's it. Okay, so it's a long equation. I need to squeeze all of it. Okay, 74.06 times 10 to the power minus 3 plus 32.95 times 10 to the power minus 5 T minus 25.2 times 10 to the power minus 8 T square plus 77.57 times 10 to the power minus 12 T to the power 3 dt. Okay, managed to get everything inside there. So what is the value that, after you have calculated? I got, just look at the temperature. You started at a higher temperature and you end up at a lower temperature, so definitely you will get a negative sign. So I got 2.8424 kilojoules per mole. Anybody? Getting
Yes.
the same? Thank you,
Same.
Aiman. Good. So write that down. That is, no, I mean, don't have to write that down. Now we total it up. So our delta H overall is equals to, now what are we doing actually? We are getting the H of the vapor of the benzene. If you look at the table that we constructed earlier, that is H3, the enthalpy 3. So I'll give it a value of enthalpy 3. That is based on the table that we have written earlier. So that's equals to H3 equals to the value of delta H1 plus delta H2 plus delta H3 is equals to 9.6066 plus our latent heat plus our final step in get, this will be negative, at 424. So what is your H3, your enthalpy 3?
37.529.
37.529. Okay, 37.529. Let me see, what did I get? Okay, I got, I just get another extra decimal point. So that's kilojoules per mole. Yeah, thank you. So we do the same thing for toluene. The one that we did earlier, this is for benzene. Yeah. Now for toluene, we do the same thing, except that now we be looking at different value of latent heat, different value of boiling point. So our toluene is going to be at liquid at the starting point temperature, then at 10 degrees C, 1 atm. The boiling point of toluene, which we jot down earlier, is 110.62, and the latent heat is 33.47. So we're going to do the same thing as what we have done for benzene. So we're going to repeat it for toluene. We're going to go at the boiling point of 110. 110.62 degrees C, toluene liquid, 1 atm. That's the boiling point of toluene, and we're going to change it to vapor at 110 degrees C, again 1 atm, and we finally will be going to the final temperature, which is still toluene as a vapor at 50 degrees C, 1 atm. Again, the same argument. How could it exist as a vapor when it's lower than the boiling point? But we're going to just assume that actually it is not a valid assumption to have it at 1 atm. But this is what we have so far. So this is a change of temperature, change of temperature, change of temperature. Yeah, this is a change of phase. So this is going to be your latent heat 1, latent heat, change of latent heat 2, that's a change of latent heat 3. So this is going to the change of vaporization, latent heat of vaporization, which if you look, which we did look at earlier, that is going to be 33.47. So we're going to write that down, 33.47 kilojoules per mole. And for your both latent heat change from step 1 is just a change of temperature. So from 10 degrees C to 110.62, your CP will be that of liquid toluene with respect to temperature. For the third step, it's going to change from 110.62 going to the final temperature. Write down the temperature. That's the CP of vapor, toluene, vapor phase with respect to temperature. So we'll be doing the same calculation as what we have done for benzene, except that now we'll be looking at toluene. So that's 10 degrees C to 110.62 degrees C. So if you look at our CPs for toluene, that is for liquid toluene, okay, 148.8. 148.8 times 10 to the power of minus 3, and the other value is for B times 10 minus 5 temperature with respect to temperature. So if you do that, what will you get? Anybody? For my answer, I got 16.9384 kilojoules per mole. Check your answer, please.
Same, Doctor.
Thank you very much. Thank you very much, Muhammad Salim. Thank you. For the third step, you do the same calculation, but different temperature, different CP, which now we'll be looking at vapor. We're going to start at 110.62 degrees C, and we end up at 50 degrees C. Your vapor, the CP of vapor phase for toluene is as written over here, which we got earlier from appendix B2. So I'm going to just write down that equation inside this integration. So 74.18 times 10 to the power minus 3. I'm going to squeeze everything so that it will fit in one row. One row. Minus 5 P minus 27.86 times 10 to minus 8 P to the power of 2 plus 80.33 times 10 to the power minus 12 P to the power of 3 dt. Right? So if you do that, let me give you my answer that I have calculated 7.448 kilojoules per mole. Again, a negative sign because you start from a higher temperature going to a lower temperature. Yeah, check your calculation. Is it the same?
Same, Doctor.
Thank you. Thank you very much. Yeah, the rest of you guys, if you haven't get the answer, try to get it. Yeah. For now, thank you. So now the overall, let's write down our overall. Okay, let me undo that. I want to look at the table first. What symbol did I give for that enthalpy? My symbol, okay, now H3 just now, I did not write it down. H3, what did I get for H3? H3 is 37.5292. I need to write down, I need to fill up in this table. 35. Did I get 35 or is it 37 just now? It's 37, sorry. 37.5292. The next value that we need is H4, enthalpy 4. So I'm going to write that here. Enthalpy 4 is equals to change in enthalpy overall is equals to delta H1 plus delta H2, change in enthalpy cap 3. Yeah. So now we're going to total it up. So this is going to be H4 is equals to overall equals to delta H1, change in enthalpy 1, change in enthalpy 2, plus change in enthalpy 3. That's, let's look at the value, 16.9384. The latent heat, 33.47 minus 7.448. You should get your H4 to be, anybody? Kilojoules per mole. Anybody? Give me a value.
$42.96.
42.96. Thank you. Thank you. I extend it to 4 decimal places. So 42.9604. Fill it up in our table. 42.9604. So our table is already completed. Yeah, we have managed to complete our table. So next, based on our to open system, you need to look at the equation of our open system now. Any term that need to be dropped off, we're going to cancel it. That's for change in potential energy, change in kinetic energy, change in shaft work. Give a reason why. It's not, you know, you cannot just cancel it off without stating the reasons. So give it a reason. So your final change of enthalpy is going to be the heat loss or the heat supply to this vessel. In this case, you're going to supply heat to it because you are evaporating the liquid. Your top stream is coming out in the vapor phase. So that means you need to supply heat to your liquid, to your feed. So that is your final equation. So we're going to write that, extend it further. Outlet, your number of mole with your specific enthalpy minus the product of your number of mole with the specific enthalpy. So since we already have the table written here, I'm going to erase this part because I'm going to do the calculation immediately below here, so that we have access to so that we have the full view of the table. Okay, or else we'll be flipping, scrolling up and down. So that's not going to help much in our understanding. So this is all the outlet. Yeah, so I'm going to, and this is the product of N time by your enthalpy. Right, so our first row, 0.4 time by the total flow rate, 6. Sorry, what am I doing over here? 0.648. That's that value. Let me change the color. That's that value. Now I need to multiply it with the enthalpy. So I'm going to multiply it with the its corresponding enthalpy, T408. So that's for our first component. The second component, which is toluene in the liquid phase. So that's its number of mole, and this is its corresponding enthalpy. So 0.648 times by the value of its enthalpy. You do the same thing for the other components, which is benzene in the vapor phase with its enthalpy. You get the product of benzene of its mole, number of mole, and the product of the number of mole with its enthalpy, 37.5292. And sorry, okay, that's done. Next, our last value, which is toluene, the number of mole of toluene in the vapor phase and its enthalpy. So 0.316 times by 0.352 and the enthalpy 42.9604. Close our bracket. So that is for your outlet minus your inlet, 0.5 for the number of mole. Why did I multiply with? Okay, I got it right actually, but I need to show to you guys step by step. Okay, 0.5 times by 0 plus 0.5 times by 0, the corresponding enthalpies. So that's done. So what is the final value of your Q? That should be in kilojoules per mole. Should be in kilojoules, sorry. Anybody? Somebody just who just said something just now?
17.664.
Thank you very much. 664? You sure? How come I got 17.9?
Yeah, doctor, I got same 17.664.
Okay, that means my calculation is off the 664. Yeah, that's kilojoules per kilojoules. But the equation asks for in joules, is it? No. Is it? Let's see the solution of the textbook. 844. Where is 844? Okay. The solution is 17.7 kilojoules. Okay, we got 17.664. That's the same when it's run off. So this is our final answer. Box our final answer. So guys, any questions? It's quite long. We solve it almost 50 minutes. Not really 50 minutes. We start at 8:20, and now it's already 9:10. So that's how long it took to solve one problem. I'm sure you cannot spend that long in the test because you need to at least solve this problem in half an hour. So any questions? Any questions? The step is very short actually. What you have to do is solve for the material balance. Remember your basis. Yeah. Then solve your energy balance using your reference state. The most important thing is what reference state you're going to use. You can use the final outlet, the outlet as your reference state, but then you have two outlets. You need to decide whether you want it to be in the vapor phase or in the liquid phase if you wanted that. Let me see whether the textbook use a different reference state. The solution in the textbook. Okay, the reference state is the same as what we have, which is the inlet. It's easier to use the inlet as the reference state. So it's all about using your energy balance, the equation, solving for Q. The part that is taking quite a long time to do is getting the CP, the integration, and using the hypothetical path to get the enthalpies. That's quite that's the part that is taking the most. The material balance is very straightforward. The equation of the energy balance is also straightforward. Just that you need to do the integration and you need to construct the hypothetical path. So any questions? Guys, any questions?
Doctor.
No, good. Anybody has anything else to ask besides this example? Okay, no, good. So let's look at our notes. We have done that. Why did I have it? Okay, that's because I need both the appendix over here. So, yeah, we're not going to do this yet because we haven't looked at the topics on latent heat. This looks interesting, but I'm not sure whether we're going to spend that long on this. So I give you guys 5-minute break. Okay, guys, we'll be back at 9:17. Okay, guys, take break. Take 5, please.
All right. Sure.
Okay, doctor.
Welcome. Hey guys, welcome back. Hope you feel refreshed after the short break. Okay, let's look at how to estimate latent heat of vaporization. So if you look at the textbook, this is the topic 8.4B, 8.4B. Right, so is how to estimate. So far, if you look at the previous example that we did, the data of the latent heat, we can get it from Appendix B1. But if it's not available, what to do? Right? So if it's not available, then we need to estimate. By the name itself, estimation is an estimation. It could be very accurate, it could be way off. Okay, the name itself is already an estimation. So let's look at this diagram. This is a phase change. You start from solid, you end up being liquid. So the change in enthalpy, that's equals to enthalpy of melting or fusion, depending on whether you're from liquid to solid or from solid to liquid, on which direction you're going. Okay? So if you are from liquid going to gas, then that will be the change in enthalpy of vaporization. You can see there's a very big difference in the change of the enthalpies. Yeah? So if you're going from vapor to liquid, that will be negative change of vaporization, enthalpy of vaporization. This will be condensation, enthalpy of condensation. Yeah. So if you for this case, from liquid going to solid, that will be negative delta H of fusion or melting, which either way you can look at it. Okay, it will be negative. Okay, if you're going from liquid to vapor, then it will be positive. Any questions? Are you guys with me? Or somebody still taking a break? I hope you guys are still with me.
Yeah, Doctor.
With you, Doctor.
Okay. Now, latent heat. Latent heat depends strongly on temperature. I did not write this down in my notes, but so that's why I got it written down now. It strongly depends on temperature. Okay, your latent heat depends on temperature, but it's almost independent of pressure. Okay. So just like I mentioned just now, latent heat of condensation is the negative of latent heat of vaporization. Same thing, if you're going from liquid to solid, it will be the negative of fusion or melting, whichever way you look at it, negative. Yeah. If you are changing from solid to vapor, that is sublimation, latent heat of sublimation. I'm not sure whether your latent heat of sublimation is given in Appendix B1. I'm not sure about that. Okay, so if you look at water, the boiling point of water is 100 at 1 atm. The latent heat of water at that temperature and pressure is 40.6. So if you have it going from, if it's condensing, then it will be negative 40.6 if it's condensing. If you're vaporizing it, then the value will be positive 40.6. That's the difference. Yeah. So how to estimate? We will look at a few equations, but if you look at Appendix B1, we have used this, so it's nothing new anymore. That is latent heat of melting. That is latent heat of vaporization. So the temperature of melting, the temperature of boiling at normal temperature pressure of 1 atm. Okay, so you can get that from Appendix B1. But unfortunately, there might be time when you don't have it, then you have to learn then you need to know how to estimate. Okay, so if you have a closed system, then you'll be looking at change in internal energy. Yeah. So again, you'll be using this equation. Change of enthalpy is equal to change of internal energy plus a change of PV. So you know about this. So if you assume either gas law, this is your final equation. Normally, change of PV is very small. You can neglect it. You can really, really neglect it. Okay? For example, we have done one example before. at 0.42 if I'm not mistaken. Wait, okay. We did this. When we did this, that is the change of pressure. The value is very small, negative 0.07. So it's very small. So go back to that note. So you can assume it's about the same. This value is very small. So it's going to be the same. Approximately internal energy is approximately change of enthalpy. So now this is the equation that we're going to use to estimate your latent heat. You have Thornton rule, you have change equation, you have Clapeyron equation, you have another equation which is Clapeyron equation, if I'm not mistaken. I don't have it written down here. Oh yeah, there. Clapeyron equation, and you have Watson equation. So these are the equations that you can use to estimate your latent heat of vaporization. Okay, so let's look at it one at a time. Your equation for Thornton, unfortunately, is the easiest, but is the shortest and the easiest, but the accuracy is only about 30%. It's not that accurate. Okay, but it's the easiest, and the equation, they are very short. So this is the equation. Let me highlight it. Oops, what did I just do? Okay. This is the equation. Okay, the change of latent heat of vaporization for non-molar liquid. How to know whether it's molar or it's not molar? Non-molar means you have the chemical is the atom is, they are symmetrical. They have even sharing of electron, even sharing. They share evenly. Okay? But unfortunately, that is not so good a rule to follow, because even though you have water over here, H over there, is symmetrical. It is symmetrical, but it is not non-polar. It is polar. This is all about chemistry, so you need to look back at your chemistry textbook. But even though it is symmetrical, but it's not polar. It's not non-polar. It is polar. But if you look at carbon dioxide, you have carbon, oxygen. It is symmetrical, but it is non-polar. This is all about electron, the sharing of electron. So you need to look back at your chemistry textbook in order to know which is polar, which is non-polar. Right? So if you have a non-polar liquid, then you have the first equation. And if you have a low molecular weight alcohol or water, then this is the second equation. Right? Let's see whether we have another. Let me look at our example. Our example is at 4.3. We need to use Thornton rule for this example. Yeah? We will go back and forth with the equation. You have a normal, normal boiling point of methanol. The normal boiling point is 337.9 Kelvin. The critical temperature is given. That's critical temperature. You will know why you need critical temperature. But for now, just take note that you have a critical temperature given, 513.2 Kelvin. You need to estimate the heat of that vaporization at the same normal boiling point using Thornton rule. So what is Thornton rule just now? Yeah, this is Thornton rule. We have two equations over here, only two. We have for non-polar liquid and for the low molecular weight alcohol or water. We are going to estimate the boiling point, the latent heat at its normal boiling point. We're going to estimate it, at the normal boiling point. At the normal boiling point of the liquid. So we were looking at that example. That example just now mentioned methanol. So you'll be using the second equation, because it's low molecular weight alcohol. So that's methanol. So let's go back. Is the equation is 0.109. Your temperature must be in Kelvin. The boiling point temperature must be in Kelvin. So let's go back to that example. Your Thornton rules in this case is latent heat of vaporization is equal to 0. Anybody remember it again? I need to go back again. Is 0.109 boiling temperature, 0.109. TB. It must be in Kelvin. Okay. So why are we using this equation? Because we are looking at methanol. Methanol is an alcohol. And that equation, if we go back to that, is alcohol, low molecular weight alcohol. Right. So we're going to use that equation instead of the first equation. That first equation is for non-polar liquid. So we're not going to use that. So let's go back to this example. Just write down the value of your boiling point. The boiling point here is that 337.9. That's the normal boiling point in Kelvin. So if you calculate that, if I look at my solution from the textbook, this is example 843. After you have calculated it, you should be getting 36.8. The unit must be in kilojoules per mole. That is the latent heat of vaporization by using estimation, using Thornton's rule. So Thornton rule. So if you look at the actual value of methanol in appendix B1, the latent heat is 35.27. We got 36.8. Well, not that far off. 35 and 37. Slight different. Yes, there is, but that's how you apply Thornton rules. Okay, any question? Anybody? Any question? Guys?
So,
Yes?
does it matter the accuracy? I mean, in the, let's say in the test or something like this, does it matter? Like here it says 30%, right?
Yeah, Thornton rules, sometimes you get it quite close, sometimes it's about 30%. I think the most is 30%. It depends. If you look at this question itself, it is stated that you must use Thornton rules. So if it's not stated, then the best would be to use the most accurate equation. So next, let's look at change equation. Change equation, if we look at the equation itself, the accuracy is about 2%. That's far better. But the equation itself is very long. Okay, so let's look at the equation. Let me try to, okay. Let's look at the equation. This is your, oh, that's too fine. That's too fine. I need it bigger than that. Okay. Okay. This is your latent heat of vaporization. Again, the unit is in kilojoules per mole. This is the boiling point. That's the boiling point. Again, the temperature must be in Kelvin. Okay, here we have an additional temperature, which is the critical temperature. The critical temperature, that's the boiling point temperature. That is the critical pressure. The critical pressure must be in ATM. The unit must be in ATM. Okay, so you're just now using that example just now as an example. You have the critical temperature here. That's the critical temperature. Yeah, that's the critical temperature. It's given. You don't have the critical pressure. So we're going to look up in appendix B1 for methanol, your critical temperature, your critical pressure is given. In fact, you don't need to use the critical temperature because it's already given in the solution, in the statement of the question. Yeah, so your critical pressure is 78.5. That is, oops. That is PC. This is TC. It's already written there. Yeah, so now let's go back to our equation. Okay, I need to copy that equation. Let me erase this first. Let me erase that. Okay. I want to copy it because I will have a problem going back and forth. So I'm going to copy it. So that's the equation. Okay. Copy. And we're going to go to that example. Yeah, I'm going to paste it. Oops. How come there's no? How come there's nothing here? That's weird. What's wrong? Let me go back to my notes. Where's my note just now? Yeah. Why can't I copy it? Let me try to copy again. Not doing very well here, guys. Copy. Okay, let's go back to our example. I'm just trying to save myself. Okay. That's the equation. Okay, so now what we're going to do, we're going to plug in the values inside our equation. Delta H vaporization is equal to the boiling point just now is the boiling point. If you go back to this, the boiling point is 64. That's in degree C, but we already have it written in Kelvin. So that's in Kelvin. We have that written already in Kelvin, 337.9. So 337.9, that's Kelvin. Bracket 0.0331. You have your bracket, the boiling point, 337.9. The critical temperature is in Kelvin, 513.20, which is from this value. Yeah, close the bracket, minus 0.0327 plus 0.0297 log PC. Your PC is 78.5. So that's your critical pressure. You're having a unit of unit of ATM. The whole thing divided by 1.07 minus the boiling point, 337.9. That's the normal boiling point. The critical temperature, 313.2. So guys, after you have done that, everything is there. Calculate the latent heat of vaporization using change equation. So what is the value? Let me have a look at the solution in the textbook. I don't have it. Surprise, surprise. I don't have change. Somebody give me a value.
I got 37.25.
5. Anybody getting a different value? Anybody? That is 37.25. Because I'm using the third edition, somehow it's not written here. If you have the fourth edition, have a look at your solution in your textbook. This is using Thornton, this is using change. By right, change should be very close, but it seems to be getting further from the actual value, isn't it? The actual value is 35.27. Okay, guys, did I make any mistake in my calculation? Somebody getting a different value? Anybody check whether that is 37.25? Anybody? Anybody getting a different value? Same value? The rest of you guys? No? Nobody doing the calculation? Ouch. Guys, are you guys with me? Anybody? Do you get the same value, 37.25?
Doctor,
Yes.
is the critical pressure given in ATM?
Let's have a look. Yes. In ATM.
Okay.
In ATM. ATM.
Or is it ATM gauges?
Oh, is that gauge? I'm not sure. Let's have a look at the appendix. Appendix. Okay, this is appendix B1. Let's see. Where's the bottom? They should write it down. There should be a statement somewhere. Is it in gauge or is it in absolute pressure? Boiling point, where is it? Critical pressure. Critical pressure. Nothing mentioned at all that it is gauge. So I'm assuming it is at absolute, isn't it? There's no mention at all that it is gauge. Can you check your solution from the 4th edition? Because I don't have the example in my textbook. My example is only right to Thornton rules and Watson correlation. Oh, yes, there is. The change equation gives a value of 37.2. This is in this unusual case. In this unusual case, Thornton rules provide the better estimate. Okay, somehow there's no calculation, but there's a statement below the solution. The change equation yields a value of 7.2. So let's go back to our example. We got 37.2. Well, the same as the solution in the textbook. The textbook did not calculate it. It just gives a statement stating that change equation yields 37.2 kilojoules per mole. But this is an unusual case whereby Thornton rules give a better estimate. Yeah, this is a different case. I mean, it's an unusual case because by right you should get better if you use change rule. The accuracy is about 2%, but instead this is quite far off from the actual value of 35.27. So the best estimate will be using Thornton's rule. We cannot say actually, isn't it? It depends on maybe the chemical itself. For this case, it's not valid. The estimate using change equation is not that good. So let's go back to our notes. Any statement? Okay, please have a look. There is this statement, hydrocarbon. The accuracy is good for hydrocarbon. Just now we were looking at methanol. Methanol is an alcohol. So if you look at this equation, it specifically specified that for molecular weight ethyl alcohol. So this Thornton is the better equation than your change equation. Why? Because change equation is specifically for hydrocarbon. It's good for hydrocarbon. But for Thornton, it's good for low methanol, low molecular weight ethyl alcohol, low molecular weight alcohol. So your calculation using Thornton is better off using, I mean, the calculation for methanol just now is better off using Thornton compared to change equation. Any question? It's specified here that the accuracy of 2% is only for hydrocarbon. So any questions? Okay, no question, I assume. So now let's look at Clausius-Clapeyron. The textbook. Clausius-Clapeyron. Where is Clausius-Clapeyron? Okay. The equation I got here is written differently from yours, your textbook. The one written in the textbook is like this. That's the Clausius-Clapeyron equation. You have vapor pressure. You have the vapor pressure. That is vapor pressure. That's all. Your vapor pressure is this. And natural log vapor pressure is equal to negative the latent heat of vaporization divided by the gas constant time by temperature plus B. So you need to plot the graph. So when you plot the graph, you will get a straight line. So this is your graph. After you plot it, you get a straight line. The straight line will have a slope of 0. This is the slope. Okay, that's the slope. That's the slope. Okay, there should not be a T over there. I need to erase. There should not be a T over here. Okay, it should be only R. Okay, should only be R. And your y-intercept, that's your y-intercept after you plot the straight line. Okay. So that is Clausius-Clapeyron equation, or you can get it in this form. This is also another equation of Clapeyron equation. Yeah, that's one equation. Or in this form, that's another one. Yeah. So Watson equation is useful when you have one value, a non-value of latent heat at the temperature of T1. When you do know the temperature, the latent heat at T1, but you need the value at a different temperature. So you use a Watson equation. To the power of 0.38. Let me tidy up because I don't want to be messy. Yeah. This is your Watson equation. That's Watson equation. You can also, it's the same thing. this equation, the bottom equation and top equation is the same thing. It's just that the second equation is in terms of with the temperature, reduced temperature. Yeah, but I think stick with the first equation would be better. Yeah. There's another equation, Clapeyron equation. When your latent heat is for Clapeyron equation, your latent heat of vaporization is constant. That's why you get a straight line. But if it's not constant, you will get a curve, for example, then you will use the Clapeyron equation, whereby you will, at a certain temperature, you will get the slope. Let's see whether we can apply this equation in our example. And now, for this example, we need to use Watson equation. Yeah, at 200 degrees C. You wanted to find the latent heat at 200 degrees C using the measured value and the estimate value. The measured value is this one from the appendix. This one is measured value is from the appendix. The estimate value is the one that we just estimate using Thornton. So let's do that. Yeah, let's look at our equation first. Where is my note? Yeah. Watson equation. Let me erase things that need to be erased because I want just the equation. Yeah, guys. Are you guys with me? Copy. Can I copy it and let's go back to our example? Yeah, so that's the equation. Okay, you wanted to estimate the temperature, sorry, I should not be using that. You wanted to get the latent heat of vaporization at 200 degrees C using Watson correlation. So I just copy the equation using the measured value. So the measured value is this at this temperature. Right, 35.27. So let's do that. 35.27 at a temperature of the normal boiling point temperature 64.7. So if you change that to Kelvin, 337.9. Yeah, so that's what I got over here. The critical temperature, we already know what is the critical temperature. That's the critical temperature, 513.2. Minus the second temperature, which is your desired temperature asked by the question 200. So if you plus that, make it into Kelvin, you get 473 Kelvin. So that's 473 Kelvin divided by the critical temperature minus the first temperature, that's your first temperature, T1, the normal temperature, to the power of 0.38. So if you do that calculation, so what is your answer, guys? Are you still with me? What is your answer? So the latent heat of vaporization at 200 degrees C is equal to what? So if we look at the answer from the textbook, let me see what is the answer from the textbook. This is using estimate. I'm using the actual, the measure value. The textbook using the estimate. So what's the answer, guys?
Doctor,
Yes.
do we multiply it by the temperature?
No,
For
this
T1
is no. This is not multiply. This is at. Sorry, let me undo that. This is at a temperature of T2 at a temperature of T1. Oh yeah, I know. I got a mistake, isn't it? Should not be here, isn't it? Okay.
Doctor, thank you.
Yeah, thank you. I just I make a mistake there. This is at. Sorry. So bring everything close to it. Let me erase this too. Yeah. Let me rewrite it. Delta H vaporization at 200 degrees C is equals to, oh dear, I just did it too close. Let me undo that. Yeah, let me undo that. That is delta H vaporization at 200 degrees C is equals to that value just now, 35 point, what did we get from the text, from the appendix, 35.27. It's multiplied by the bracket, not multiplied by this. Do not multiply that. Do not multiply this. Thank you very much, Aiman. So what's the answer?
20.15.
Sorry?
20.15.
20.15.
Yeah.
Thank you. It's kilojoules per mole. So that using measured value. So now we do the same thing, but using the estimate value that we got earlier, which is the Thornton equation. Yeah, we do the value from Thornton equation. We got 36 point, that's the value, 36.8. 36.8. We repeat the whole the whole thing. So be careful, guys. Do not put the temperature in front of this temperature here. Please remember that. So what's the answer? If I look at the solution, it's 21 kilojoules. This is from the textbook. I'm not sure whether it's going to be that accurate because normally the textbook just round off the value. So what do you get? This is using measured value. This is using estimate value. This is using estimate from Thornton. Anybody getting a different value? Because I just got that that value from the textbook. I'm not sure whether you should be exactly the 21. I'm not sure. It might be round off. Anybody?
Same, doctor.
Same. Good. Okay, guys. So this is how you estimate when you don't have any data available for latent heat. This is how you do it. So it depends on which one will give you the best accuracy. Which equation give you the best accuracy. So in our example, methanol, the one that is more accurate would be Thornton. Not Chen's equation. Chen's is more towards hydrocarbon. Okay, guys, any questions? Any questions? Again, let's look at the equation. We did not use Clapeyron or Clapeyron equation at all because you need to plot. You need to plot it. Anyway, let remind you guys that the R constant that you need in this equation is 8.314 joules per kilomole per mole. Okay, that's the gas constant that you need for that equation. So far, we have looked at Watson correlation, we have looked at change equation, and we have looked at Thornton equation. So if you need to use Clapeyron or Clapeyron equation, then you need to plot the graph. And lastly, before we end for today, you can also estimate the heat of fusion. The heat of fusion is the heat of melting. So this is how the equation that you can use. You have three equations. If you have a metallic element, if you have an inorganic compound, or when you have an organic compound. Very straightforward calculation. Only three equations given. I'm sure there's more than that in the other references, but in your textbook, there's only three equations given for estimating the heat of fusion or heat of melting. Okay, guys? Any questions? We have done 841, example 841. We have done 842. We have looked at 843 just now. So, okay. We have done this. 844, we have done it. There's another example here. If you want to do on your own, I have the answer given here. So you can try to do it yourself. This is how to estimate the heat of vaporization of benzene. See whether you get the same answer. Okay. Okay, there's another Antoine. This is another something to do with Antoine. But this is a bit, I'm not sure where I got this problem from. I'm not sure. There's one example here. This required heat balance. This required heat balance, outlet temperature, cooling rate, which is Q. You need to find the temperature of the outlet. That's quite long. This example is very long. There's another example. Okay, this is similar to what we have done just now, benzene and toluene. Okay, guys, it's almost similar. It's very similar, in fact. You would need to find V, you need to find L, and then you estimate the heating. Okay, now you have extra problem to solve for. The mole fraction. That's a bit complicated here. You have the mole fraction that you need to solve for, the vapor composition. Yeah. Okay, guys, that's it for today because it's already 9:52. Let me unshare this so that you, for those who haven't scanned the QR code, let's see whether you guys can still scan it. Let me go back to my, where is my QR code? Oh, no longer here? Okay. Okay, for those who haven't scanned, you can scan it now. Okay, for those who already scanned, thank you very much. See you guys tomorrow at 2 p.m. Assalamualaikum warahmatullahi wabarakatuh.
Thank you, Doctor.
Doctor.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.
Most welcome. Thank you, guys.